Hey physics friends, and welcome to 4.2, which is using Newton's second law, F equals ma. We're going to be focused today specifically on this law. And this law says if you increase the force, you increase the acceleration. If you decrease the force, you decrease the acceleration. That's directly proportional. When one goes up, the other goes up. If you increase your mass, then you decrease your acceleration. These are inversely proportional. And I kind of equate these to the master sword. F equals ma is probably the most important equation that you're going to learn. No, it is the most important equation you're going to learn in high school. There's another really great equation. You've all seen it, E equals mc squared. It's Einstein's. It means that energy and mass are interchangeable. And that's a really crazy idea. I don't know if it makes sense to you. It shouldn't make sense to you if that makes any sense to you. But I have a collection of really cool science tattoos that you'll see in a book that I have in my class if you'd like to flip through and see some other ones. But suffice to say, this idea is super important. I actually label it as the master sword here. The Master Sword in The Legend of Zelda is very, very important. And I want to give one caveat to it. I want you to use the net force. And if you have this idea, this is going to take you very, very far. This is a very, very important, probably the most important idea of Chapter 4. That if you have a net force on an object, then you have acceleration. Let me give you an example. The Master Sword. I have a box, and there's some friction going on here. I'm going to push on this box. You can see that I'm pushing with 200 newtons. Friction is opposing me with 125. So, 200 minus 125, I have a net force of 75. If I have a net force, then I have acceleration. Do you see it? Net force, acceleration. If I don't have a net force, let's bring this down. There. Now I'm pushing with the exact same force as friction. If I don't have a net force, my net force is 0, then I don't have acceleration. That doesn't mean I can't have movement. Mr. Hare, how can you be moving if you're pushing with the same force as friction? The answer, sometime in the past, I had to overcome friction to accelerate myself. And you saw it just 5 seconds ago. I was pushing with 100 and I think it was 150. If I have a net force, then I have acceleration. If I don't have a net force, then I don't have acceleration. And you'll see it right here. There's no net force. That means there's no acceleration. A former student of mine, Ben, said it best. Acceleration, force doesn't affect velocity, and force doesn't affect position. Force affects acceleration. So I'm pushing with the same amount of friction. Am I moving? It depends. Did you get yourself moving in the past? And so now that I'm moving, I'm just not accelerating. Or I can reset this thing, and I can push with 94. Oh, it's going to be tough. Here we go. Here's 94. Here I'm pushing with 94. And then now I'm not moving because I haven't overcome friction at this point. I have to first overcome friction to get myself moving. And then when I equal to friction, then I won't be accelerating. Now my acceleration is 0. Now I can accelerate or I can decelerate. Check this out. Here's an interesting concept. There is a net force. and the net force is pointing backwards. So that means that there's acceleration backwards. I'm slowing down. This thing is moving to the right. Its velocity is positive, but the force is negative. The acceleration is negative. You'd have no idea what the velocity is going to do, but what you do know is that it's decelerating. So here are the big ideas. If there is a net force, then we have acceleration in the direction of the net force. And you saw that right here. I'm going to have a net force. Net force. I'm accelerating forward because my net force is forward. Now I can decelerate. My net force is backwards, so my acceleration is in the direction of the net force, slowing down. We can switch these words around. If there is acceleration, then you can conclude there's a net force in the direction of that acceleration. Whatever way it's accelerating, not whatever way it's moving, be very, very careful. Whatever way it's accelerating, look for the acceleration. If it's accelerating forward, then the force in the forward direction is bigger. If it's accelerating backwards, the force backwards is bigger. The thing is moving forward, Mr. Hare, so the forward force should be bigger. Well, let me show you an example opposite that right here. The thing is moving forward, and there's no force pushing it forward. There was, in fact, force pushing it forward in the beginning to get it there, but now once I let go, there is no force pushing it forward, but yet it's still moving forward. It's like a ball. You throw a ball in the air. Why is it moving up when there's no force up? Well, it's just objects in motion stay in motion until the force acts on them, and then they're decelerating and they come to a stop, and now friction stops. My forces are equal to 0. You can say this. If there's no net force, the opposite of this one, if there's no net force, then you have no acceleration. No net force, no acceleration. Again, that doesn't mean that there's no movement. There's no acceleration. So here, I can have a net force, remember from before, if I have a net force of 0, so there's no net force right now. If I can get 94. There's no net force, but there's motion. If there's no net force, there's no acceleration. That's the main idea. That's the big idea from this whole thing. That if there's no net force, there's no acceleration. The acceleration is equal to 0. And if you have no acceleration, then there's also no net force. All right. These statements are super important. And you always look for acceleration. If there's no net force, then there's no acceleration. If there is a net force, then there is acceleration in the direction. Let me show you how Newton's second law, like the actual F equals ma, works in here. So we're going to reset this. I'm going to take away all the friction. None friction. Remember, the net force is all the forces. There are two forces at work here. I'm going to push on this. Let's push on it with 100. I'll pause this. So I'm going to push on this with 100 newtons of force. Now, there's no friction, so that means there's no force going back this way. There is gravity. But there's also a supporting force provided by the ground, and those are canceling out for right now. It doesn't matter what this thing weighs, and there's just suffice to say that there's an upward force. So all the forces on this object, this is the only one left over. And my push force is 100. The mass of this is 50 kilograms. So what should my acceleration be? 100 divided by 50 is 2. So when I hit play, you'll notice my acceleration is 2 meters per second. If I increase my push to 200 newtons, 200 divided by 5 is 4. And you'll see that this went to 4. Now, if I increase this to 300, maybe even 400, my acceleration is going to be equal to 400 divided by 50 is going to be 8. And then I can't run that fast. And now look what happens. Objects in motion stay in motion in a straight line forever unless acted upon by a force. We're not including air resistance here. We're just assuming that there's no air resistance to slow this down. There's no friction to slow this down. So this thing will keep going for eternity in that direction until maybe we have a little friction. Now, if we have lots of friction, this thing's going to slow down very fast. And you can see my speed decreasing pretty rapidly. But if I don't have as much friction, that speed doesn't decrease nearly as rapidly. But if I take away all friction, it will just stay at that constant speed forever. Right? Let's do this. Pause it again. Now, I'm going to double the mass. Right? Now the mass I'm pushing on is 100. What if I push on this with 100? So my acceleration should be 1 when I let this go. And you'll see it. There it is. 1. What if I increase friction so that it's exactly equal to my push? Now, over here, all the forces on my object. Now, I'm going to say that forward is positive. So I've got a positive 100. I'm pushing it forward at 100. And friction is opposing me at a negative 100. So 100 minus friction, which is 100, that's going to be 0. And then 0 divided by 100 is still 0, so my acceleration is going to be 0. When I unplay this, you'll see that I'm now moving at a constant speed. So here I'm putting numbers to these concepts. That when there is no net force, right now there is no net force. If there's no net force, then there's no acceleration. If I do have a net force, I increase my force. Now my push force is 200, so 200 minus 100, and my mass is 100 times my acceleration. So 200 minus 100 is 100. 100 divided by 100, that acceleration is equal 1. Now this is going to accelerate. And you'll see there's my acceleration of 1 meter per second per second. And again, I can increase my force. Now I'm still accelerating. I can only run so fast. And then I trip and fall. And I'm going to slow down. Right? You'll see the speed decreasing. If I increase friction, it's going to decrease in speed faster. If I take friction totally away, it's going to slide at that speed for eternity. All right. So let's do a couple of example problems with these ideas. Back in your notes, you'll see this problem right here. It says, Anjuta is holding a stuffed dog with a mass when Sarah decides she wants it and she tries to pull it away. Sarah's pulling horizontally and Judah's pulling horizontally. What is the acceleration of the dog? So we're going to make a free body diagram. I want you people to be making pictures. Label your forces. She's pulling it. Sarah pulls it with a force of 10. So I don't think it matters which direction Sarah's pulling. She's pulling with 10 newtons. And Judah's pulling with 11. So I'm going to make that force bigger. I make my forces in red. And then I'm going to label the mass of the dog in green. So when I do this problem, I'm going to go F equals ma. Now it's the net force. And remember, the net force is all the forces. So all of the forces, I have to say which direction is positive. I'm going to make to the right positive. So I've got a positive 10 and a negative 11. The mass is 0.30, and then I can solve for my acceleration. So 10 minus 11 is negative 1. So then I'm going to take negative 1 divided by 0.3. So my acceleration is negative 3.33 meters per second squared, or you can say the acceleration is 3.33 meters per second squared in the direction of Anjuda. Anuja's direction. The negative tells you what direction it's being accelerated. So if positive is to the right, it's definitely being accelerated in that direction, right? There is a net force, so we do have acceleration in the direction of the net force. Here's another example. There is a person standing on a bathroom scale. Your mass is 75 kilograms. And you are elevator starting from rest. The elevator accelerates upwards. That's huge. You're accelerating upwards at 2 meters per second squared. What that's telling me is this. When you accelerate up, there is acceleration. So that means that there's going to be a net force in the up direction. So I know that this force of gravity here, this force right here, which is the normal force, is going to be bigger than gravity. She's standing on the ground. The supporting force by the ground is bigger than gravity. That can happen. And that's what's causing this acceleration of 2.0. So how do we use this equation? To say this. Is the scale reading greater than? So number one, I know the scale is going to read greater. The scale reads what the normal force is. The scale is going to read what the normal force is. For instance, when you're standing on flat ground, the scale reads what you weigh. But imagine being dropped off a building and you put the scale underneath you as you're falling, it's not going to read anything. Just because you have a weight of something doesn't mean you have what the scale is going to read. I think this is everything that this problem wants to know. I think that we're done right now. So this problem could be a little bit different, I suppose, if they said during the constant speed. Because you can see in the problem, they accelerate for 2 seconds and then they move at a constant speed. So what if the question said during the constant speed? If you're during the constant speed, that means that your acceleration is 0. So if there's no acceleration, that means that there's no net force. And that means that this force is going to be equal to gravity. So whatever gravity would be equal to, that would also be your normal force. How do you find gravity? If you want to find the force of gravity, then you take the mass times the acceleration of gravity. It turns out that the acceleration of gravity on Earth is always 9.80 meters per second squared. So since this person's mass is 75, if you take 75 times 9.8, you get 735 newtons. So this person is 735 newtons, right? Going back to the initial question, what if it said, what does the scale read? Your net force, all forces. We have to pick what direction we want to be positive. I'm going to make up positive. That means that the normal force is a positive number and gravity is a negative number. My normal force, I don't know. But I do know gravity now. My mass and my acceleration. And since my acceleration is up and up is positive, this acceleration is a positive 2. So 75 times 2 is 150. 150 plus 735 would be 885. If this question says, what does the scale read? The scale reads 885 newtons. And it should read more than my original scale because I'm accelerating upwards. So just a little bit extra tacked on to put some numbers to these concepts. Remember, very important, if there's a net force, then there's acceleration in the direction of that net force. And if you have a mastery of that, it lends itself to these equations very easy. I mean, it makes this math, like, because people are like, oh, this is so much math. It's not that difficult of math. It's just the concepts are difficult. Which one's positive? Which one's negative? Which ones do you put in? Which ones do you not put in? When do you have friction? When do you not have friction? When is there a push? When is there not a push? It's the whole idea of the concepts at work here that really get people. Talk to you later, physics friends.